Okay, welcome to the Forum on Robotics and Control Engineering. Hi, everyone. So my name is Tansel Yucelen, and I am an associate professor at the Department of Mechanical Engineering at the University of South Florida. With the support from the university and IEEE Control Systems Society, I am very proud today to host Dr. Anthony Calise, and he was a professor of aerospace engineering at Georgia Institute of Technology, and also he was my PhD advisor. So it is really an honor to host him today in our live seminar series on control systems through the FoRCE. I would like to mention a couple of words about the FoRCE. Basically, FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the globe. To support this mission, we periodically invite distinguished lecturers like Dr. Calise to give talks on recent research results related with controls and robotics. I am almost done, but let me mention a few words about the Microsoft Teams. We are all muted during the presentation. Please ask questions after the presentations. You can simply unmute yourself or use chat so that I can read your questions to Dr. Calise. And this session is being recorded to be posted to the FoRCE website. So I just wanted to mention about that. So once again, I am very proud today to have Dr. Anthony Calise. He received his PhD degree in electrical engineering from the University of Pennsylvania in 1968. In addition to Georgia Tech, he has involved as a co-founder and chief scientist with Illuminati Aerospace. Before that, Atir Aerospace. And before Georgia Tech, Drexel University, he was a professor of mechanical engineering. And he also worked as a senior analyst at Dynamics Research Corporation, as a senior engineer Raytheon Missile Systems Division. And before that, he was an assistant professor at the Veterinary University. So for all of you who are here live for the presentation of him, I first would like to thank Dr. Calise for participating in our forum. So Dr. Calise, whenever you are ready, we are ready for your presentation.
Tansel, thank you for that kind introduction. I'd like to also thank the organizers and all the background work involved in making these presentations possible. And I'd like to thank everyone in attendance today. This talk is about one of the main areas of research that I was engaged in during my tenure at Georgia Tech. And I'd like to invite you to write to me afterwards if you have any questions or comments. You can see my email address there on the first chart. And I'd also like to say that if you download a copy of the presentation, can you hear me? I'm sorry.
Yeah, we can hear you well right now. I think one of the attendees forgot to mute themselves. Now we are good. Okay.
So the last thing I want to mention is if you download the presentation, you'll see there are links to all the video files, but in my experience, they only play if you copy and paste them into Google Chrome. So I'd just like to mention that up front. Okay. So the first question is, why make flight control systems adaptive? I mean, you know, we've been flying airplanes for a long time now that do not have adaptive autopilots. Why do we really need them? And one of the goals in adaptive control, or what I actually have here is a list of objectives for adaptive control. You want to maintain regulation, command following, disturbance rejection in the presence of a lot of nasty things like modeling errors, unmodeled unknown dynamics, upset recovery from unknown failures in propulsion, actuation, or airframe damage, control limits, nonlinear actuation, time delays, sensor noise, et cetera, et cetera. And I'm going to try to illustrate some of these points during my talk. One of the disappointing things about adaptive control is there have not been very many transitions into real flight control systems. And one of the major obstacles that anyone working in this field will encounter is the project manager is going to ask, why can't I just use legacy design approaches based on linear theory? Why do we need an adaptation? And then how do you certify adaptive control systems? You know, things like gain margin, phase margin. What's the effect of sensor noise? What about control limits? So the key question boils down to, how do we certify adaptive flight control systems? That's a major stumbling block. This chart illustrates a number of flight demonstrations we did while I was at Georgia Tech. We were involved. Most of our funding came from the Air Force Research Lab, and also at Eglin Air Force Base, and also from the Air Force Office of Scientific Research. But there were also government fundings and things like that as well. Anyway, there's a key difference between doing flight tests and actually doing what's called a technology transition. Technology transition means you've gone all the way and you've transitioned the technology into an existing system, and those systems now are flying with that technology. So the only example that I'm aware of that in which, you know, I mean, adaptive control has been around since around 1980s, early 80s, maybe even earlier than that. But the only fully transitioned example that I'm aware of is the JDAM family of guided munitions that you see here on this chart. Okay, so I'm going to say a few words about that and why that transition actually occurred. Well, first of all, let me tell you a few words about JDAM. JDAM is a guided munition. What it really is a tail kit. Oh, so all the intelligence is built into this tail kit. And so the idea is you're able to strap this tail kit on different bombs. The problem is that the JDAM has to fly at extremely high angles of attack to get the range. So it's typically released at around 35,000 feet. And it's a precision guided munition. And so what they've learned is that when you design this in a traditional fashion, if you design the autopilot in a traditional fashion, it's necessary to gain schedule the autopilot as a function of three variables: Mach, altitude, and angle of attack. So these little dots represent the points about which you linearize the dynamics and design a control system. And so that means you have a set of gains, roll, pitch, and yaw. And these gains vary and are interpolated between each of these design points as the JDAM descends. Okay, so that's how it was done in the past. And so the problem they ran into was that every time you had to move a tail kit from one bomb to another, it took almost 9 months to a year to accomplish that, because of the fact that you had to tune so many gains, you had to do so many flight tests, you had to do so much wind tunnel testing. It was extremely laborious and time consuming. And that was no longer acceptable to the military. And so that created an opportunity for adaptive control. And so today, all JDAMs fly with an adaptive autopilot that require no gain scheduling, no tuning. They work out of the box. You move the tail kit from one bomb to another, and everything works well. So I have a little video here of our very first flight test demonstration. Now, let me say before I show the video, the autopilot was designed in my laboratory at Georgia Tech, working with my graduate students. And it took us about 4 months to design the adaptive autopilot. And we were only given flight test data for one bomb at a single flight condition. And in fact, the bomb that was actually flown was not the bomb that we were given the data for. The third thing is that in the JDAM tail kit, even though it has 4 fins, only 3 fins are actuated. So this means you have to very precisely control the roll angle, because the data, there's a very nonlinear dependence on angle of attack, and the data provided was only for a single angle of attack, positive angle of attack. And then in the flight test, they did something without telling us. They actually, Boeing conducted the flight tests, and they actually committed negative angles of attack, which was never done before during the drop. So I'm just going to show you quickly here an example of what a JDAM drop looked like. That's an F-16 at around 35,000 feet releasing the bomb. And I'm going to move this quickly ahead so that you see the target area, and you see it was very accurately engaged the target at the end. This was all done in Air Force Base. There's a side view here as well. You can see the bomb entering at a very steep angle, which is necessary for penetration. Okay, so down to control system architectures. What's this all about? So the blue boxes here represent what is traditionally done. So you have a nonlinear plant, you linearize the dynamics. This means you come up with A matrix and a B matrix, shown down here. And you use that A and B to design a linear controller. Okay. So the other portions of this diagram are what's needed to adaptively augment this linear controller. So you need a linear plant model for the behavior, which is based on the linearization of this plant and the action of the linear controller. So it's a closed loop model of the behavior. You can think of this as the desired behavior. So it has this form of differential equation, and then the other elements here is the sensor noise filter, which is essential. You form an error signal between the actual plant response and the model response, and this is used to train the neural network. So that's basically what's going on, without getting into too much detail. So why neural networks? Well, the key is that they are universal approximators. And the word neural here is used to indicate that they're somewhat modeled or chosen to represent the way our brains function. You know, we have neurons, and neurons fire, and they interact with neighboring neurons. So we don't really quite understand all of that, how it works. But this architecture for neural networks was chosen with that in mind. So it's made up of a sigmoidal, what we call basis functions. It's these little circles here. This is a single hidden layer neural network. You can have multiple layers if you so choose. And each neuron receives signals from the inputs. And there are weighting functions. This V is a matrix of weights, allocating the strength with which each of these inputs are entering this function. And then you have weights at the output side to the output of the neural network. So the sigmoidal basis functions behave as shown here. So they don't do much unless the signal level gets large enough. And so they fire more or less. You can think of this as a network, neural firing. Okay, so in neural network-based adaptive control, what you adapt are the weights in this matrix V and this matrix W. And so I'm showing you a typical form of the weight adaptation when there's only the output weights are adapted. And the point, we don't really need to get into the details. The key point here is, though, that it's a differential equation for W, this matrix W. And so that means you have to numerically integrate this equation. And you know, this is the error signal that I mentioned earlier that's feeding this equation. And P is a matrix that's a positive definite matrix that satisfies the Lyapunov equation. So in designing a neural network, you get to pick the adaptation gain gamma. You get to pick this. This is a modification term called E modification. That also has a gain. And you get to pick Q. And you pick Q, you solve for P. And you also have to select these basis functions, these forms here. Okay. So what's the key assumption in all this? The key assumption is that there's a set of ideal weights that, and those ideal weights are constant. So this is the key word here, constant ideal weights that you're trying to adapt to. Okay, I'm not going to go through the details here. This is not really much detail. But I just simply want to say that adaptive control is based on the Lyapunov stability theory. And if you are familiar with that subject, then of course you don't really need to look at this chart. But if you're not, I put this chart here just to list, if you want to start reading references, for example, Slotin and Lee, applied nonlinear control. This will give you an outline of the key points to look for in investigating, learning about Lyapunov stability theory. And that theory then is applied to adaptive control. And this chart I put here, again, taken from chapter 2 of reference 34. And by the way, I forgot to mention all the references I am citing on these charts appear at the end, and you know, that there's a long list of references at the end of the talk that I'll show you. Okay, so this sort of outlines how it applies and what the idea is in Lyapunov stability theory. So again, I'm only providing this for those of you who may not be familiar with how one comes up with this adaptation law using Lyapunov stability theory. And this is sort of an outline, a guide, if you want to start looking into it. Okay, so another very important topic that we originated, I should say, one of my graduate students, Eric Johnson, who's online today, I think, this idea of control hedging. So what this does is allows an adaptive controller to function even in the presence of control, things like actuator dynamics and unmodeled actuator dynamics and saturation. So without this, an adaptive controller would just go crazy if indeed the actuators did saturate. So the idea of hedging is to subtract a signal, a hedge signal, from the plant model that's being used to form this error signal, which in turn is used in the adaptive law. Okay, so the model for the actuator dynamics and saturation are included in this block, and you subtract that from the command U and you form a hedge signal. And without this, I mean, the adaptive controllers could very rapidly go unstable. And so again, the references to this topic are cited up here, 15 and 22 to 24, and they're all given at the end of the talk. So here's an example. This is an actual flight test result with our R-50 helicopter, which we had at the time. And it shows what happens when you have time delay, for example. You have it's a high bandwidth design, out to 10 radius per second. And you have actuator rate and position limits. And this shows an actual flight test result. The green line are the commands and pitch attitude, and the red lines are the responses with the adaptation. And this is without hedging. And then when we engage hedging logic, you see that we get a very nice command following. Here's a picture showing Eric Johnson on one of our flight vehicles, and then also Girish Chowdhury, one of my former graduate students. Eric Johnson now is at Penn State, and Girish is at University of Illinois. They're both professors there now. And one of the flight tests that we did was with this adaptive flight control to demonstrate the benefits of adaptive control when you have a major catastrophic structural damage. We actually blew off 50% of the wing, as you can see here, during the flight. And that means, of course, you lose a good bit of the aileron control provided on the wing surface on one side. And I'd like to draw your attention to this portion down here showing the wing being blown off. And what happened to the controls, rudder, aileron, and elevator, after this occurred as a result of the adaptation that occurred to allow the aircraft to continue following this pattern of command pattern in the flight. So this shows it still did a very good job of flying the waveform, as you can see, a commanded pattern, even after the wing was blown off. But it entails a very complex behavior, including saturation down here, as you can see the saturation occurring. And particularly the rudder and aileron behavior to accommodate this failure that took place during the flight. So I'm going to show you the video now. It's over here. You'll see the wing being blown off, and then the aircraft continuing to fly this pattern quite nicely. And it actually landed that way as well, of course, so we didn't lose anything. And that gives you an idea of the power of adaptive control. But of course, the key element here is that one must accommodate also nonlinearities in actuation, particularly here due to saturation. Okay, let's see. This is another laboratory experiment Ali Kate, who's also attending today, did while he was a graduate student. I guess he remembers this well. This was a little model that we used to illustrate the benefits of adaptive control in the laboratory. And what's shown here is a traditional linear model for this system. It models the motor and it models the pitching motion of the arm when the blades are turning. This also can do turns as well by differentially commanding the rotors. And what we found out was that if you design a control system using this model, it doesn't behave very well. And it's largely because of unmodeled effects, in particular friction that occurs in the model. So I'm going to show you a little video of how this behaves with and without adaptation. So you'll see during the video when the network is on and when it's off, and what the behavior is like also under saturation. So at this point, the neural network is on and it's following these square wave commands quite nicely. Then we turn the network off, and you see it goes into this oscillatory type behavior, unmodeled effects and saturation. How many effects due to the friction? And then it even hit the bottom there, quite nasty. Then I turn the network back on again, network back on, and now it recovers and it's starting to follow the commands. And here Ali is showing disturbance rejection. He introduces a disturbance, and then he drives it into saturation. And you see the network doesn't go crazy. It does recover from that temporary saturation to follow. Okay, so here are the experimental results being plotted. But this is a different experiment where we're commanding a kind of random motion in pitch. And this shows the behavior with the network off and hedging off. This is what we got with the network on, but hedging is off. So you see, without hedging, the neural network isn't able to track very nicely the commands. And then the network is off now, but hedging is on. And that doesn't help either. I mean, it's a little bit better, but hedging does not help when there's the network is off. But when you turn the network on and the hedging on, we get very excellent tracking of the command profile. Okay. We did a lot of work in output feedback. So in other words, what do you do when not the entire state of the vehicle that you're trying to control is available for feedback? And so we call this, of course, output feedback control. And the design, I mean, the architecture, it looks very similar, except now you have an output you're trying to follow, a command you're trying to follow. And you have a linear control that only uses the sensed variable y. In other words, x is not available for feedback. But the architecture is very similar. And there's this theory that goes along with this. And again, the references here are 16 to 21. So here's an illustration of that. We have a 3 discs shown. This is, again, a lab experiment. There's a disturbance, a motor used to introduce disturbance to this upper disk. This is the Y that we're trying to control, at the position of this center disk. This is the thing that's actually being controlled. So this is just a sensor right here. This is not we're only using the sensed position of this for feedback. And this is where we're introducing the control in this bottom disk. And the control was designed assuming that this is all a rigid rod. So it uses the transfer function shown here, only this portion of the transfer function. Whereas in reality, because these are flexible lines, you've got modes. And this shows the mode shapes that are present in the system. And this is a Bode plot, magnitude versus frequency of the amplitude of the transfer function. If it were indeed rigid rod, it would just be this dashed line here. But in reality, you've got these modes present in the Bode plot, open loop Bode plot. So the linear controller is designed using this simple model, and it's a you know, a lead compensator basically. So it's this is the transfer function of the controller, and it presumes a rigid model. So this is the simplified model of the plane. Okay, so I'm going to show you what that looks like when we applied that control design. So first, let me show you what's going to be happening here. The linear controller. It's a linear quadratic Gaussian design, LQG design. So it's going to be first off. So it's open loop here for the first 20 seconds. Then the next 20 seconds, we turn on the linear controller, and you'll see how the system behaves. And then we'll turn on the neural network in the next 20 seconds. And then we command square wave. I had to track a square wave without the neural network. And then after 80 seconds, we track the square wave with the network turned on. So that's what you're going to be seeing during this series. So, and the thing you want to look at is this center disk, because this is the thing we're trying to regulate. So you see, there's no control at this point. So there's a random disturbance applied up here, and it's completely open loop. And that's what it looks like. So now we turn on the linear controller, and you see it behaves a little bit better right here. This is the control signal. This is the theta 2 is the position of this upper and middle disk. So it's still oscillating around like that. And now we turn on the neural network, and you see that response in theta 2 gets much smaller. And you can see it here too as well in the picture. There's very little motion now in this center disk. Okay, and now we introduce step commands. So we want theta 2 to go up to the step, but this is without the neural network present. So the response in this blue line or green line, whatever, is not that great. And then at 80 seconds, we turn on the neural network, and you can see here the tracking performance is significantly improved. So we're doing this to illustrate the fact that even though we have a very poor model of the system, we've ignored all the flexible modes, we can still track a square wave command quite nicely. Okay, there's another topic area. It's called adaptive loop recovery. Now, this is extremely important from the perspective of preserving the gain and phase margins of the reference model. And again, this is also very, very important if you're trying to certify a flight control system, because you can claim with adaptive loop recovery that you preserve the gain and phase margin of the nominal design. And this was something that the first topic area I gave Tansel to think about when he first came to work with me as a graduate student. Again, there are references. The key reference to this topic area is number 30. And this is a flight demo of adaptive loop recovery. So in this demo, we're intentionally introducing a time delay of 0.14 seconds in the flight for a short period of time. And in this green shaded area here, this is the flight test response. The ALR is turned off, adaptive loop recovery is turned off, and then turned on again, and you see the behavior and the pitch rate recovers because of this ALR method of augmenting and adaptive control. So there's a little illustration here of the flight when that occurs. So you'll see the aircraft start to pitch a lot. This is the ALR turned off and then recovered. And then another area where adaptive control can play a very important role. These days, there's a large movement towards implementing and designing new aircraft that are either augmented with or don't actually augmented with a flow control device, or they can be used to completely eliminate the need for moving control surfaces. And the question is, what would new designs look like if you had this capability installed? And so the idea is that you use an array of active flow control devices. You distribute them along the wing surface. And there's basically two types. One is called synthetic jet, where you have a disc that vibrates. So there's no net flow of air, and that's why it's called synthetic jet. And you have distributed bleed, where you suck air in and release it up in the front, and you can affect the lift on the wing surface. Now, the reason neural networks can play an important role here is that really you're now talking about an array of sensors, an array of actuators, rather than single actuators and single sensors. And so the idea here is to treat this array, design a nominal control where you take the average effect of all these elements into account, but then augment it with a neural network that can individually take into account the differences between these sensors and actuators based with the behaviors of these sensors and actuators based on their locations on the surface, which are unknown, by the way. I mean, it's very difficult to model the differences between a sensor based on its location on the wing surface from another sensor. So, but a neural network can take that, is especially useful in feeding in all these inputs and providing individual outputs to each sensor and to each array element, actuation element, by augmenting the nominal control design in that fashion. So we have both laboratory and flight test results to illustrate this behavior. This shows the fact that we can move surfaces in a tunnel. And here it's a vibration. The goal is to remove this vibration caused by the fluctuation in the airflow. And you can see that the vibration essentially goes to zero without any moving control surfaces. It's all done with synthetic jet actuation. And this here shows that we can Harry Glazer designed and operates these wind tunnels, and it did all the work related to synthetic jet and distributed bleed actuation. And this is a flight test we did without any moving surfaces. Sure. Okay. I'm going to wrap things up by pointing out two deficiencies in adaptive control. One is the case of time-varying ideal weights. Now, remember, I said at the beginning of the talk, one of the underlying assumptions in adaptive control is that the ideal weights are constants. They're unknown, but they're constants. But what happens if you should have a time-varying ideal weight? So the uncertainty delta here has some W of t times x rather than a constant weight. And WT is, in this case, a square wave having a period of 5 seconds. The second deficiency I want to point out is the case of proportional plus integral control. Now, many flight control systems are what we call P plus I controllers. They involve proportional and integral terms. And the reason for that is that one of the nice things about PI control is that you can have command tracking with zero steady state error, even in the presence of constant disturbances. So that's why they're employed, basically, in flight control design. So in this case, the W is constant, it's this 1 and 5 here, but there's an integrator state to implement the PI control. So this is a second deficient. This leads to a second deficiency I'm going to point out. So here we are in the first case where this shows performance of a nominal control in the presence of time-varying uncertainty. So nominal means there's no adaptation. And so here's the square wave command, and the response looks like this. So in this case, the adaptive signal is 0 because there's no adaptation. And this is the delta that goes along with that response. That's the uncertainty in the system. Okay, and then the ideal weight is the square wave, as I mentioned before. And the estimated ideal weight is 0 because there's no adaptation. So now if you turn on the adaptive controller, in this case, and I'm showing results for two sets of adaptation gain here, gamma 10 to the 2 and gamma 10 to the 4. So the dashed line is 10 to the 2, and the dotted line is 10 to the 4. And you see what happens here is, okay, so now you're able to track, but it's kind of like a wavy tracking, as you can see. And the other thing is that things get very noisy in the adaptive portion of the signal. It gets very noisy at this high adaptation gain, 10 to the 4. And this shows its estimate of the weight. So it's estimating it, but it gets a very wavy kind of estimate. And at the high adaptation, the estimate gets very noisy. This is the second deficiency. This is with the PI controller now. So here we have a constant ideal weight, but it's a proportional plus integral controller that we're augmenting. And there's, again, I'm showing for two different adaptation gains here. The tracking performance is not that great in the first 5 seconds, but eventually starts to do a pretty good job. So the point is that should you have a situation where there's an upset in an aircraft, you may not be able to tolerate this long duration of adaptation that occurs because it's a PI controller. So basically what's occurring here is that, remember, in adaptive control requires integration. And that integration, numerical integration of the adaptive law, can conflict with the integration occurring in the nominal controller. They may actually be opposing one another for a period of time. So this shows a second potential deficiency. So this, all of which leads us to the main thesis topic area of Professor Yucelen. When he came as a graduate student, this was the main subject of his PhD thesis. derivative-free adaptive control. In other words, can we have adaptive controller design that does not require numerical integration to obtain the ideal weight history? And so he called it derivative-free adaptive control. And we actually have a book on this subject now that just appeared this past month that goes through the theory. It also covers a lot of experimental results and talks about potential future research in this area. So here's a Tansel, I guess this is his current crew of graduate students and lab assistants at this time. And what is derivative-free adaptive control really about? Well, again, I want to point out there are references to this topic area 31 to 34 at the end of the talk. But here's the form. It does not involve a differential equation anymore. It involves a delay equation. And so WT is some gain matrix times WT minus tau. Tau is the time delay. And then an adaptation term. And you can also have, for example, I'm illustrating here adaptive loop recovery term in this design, but you can also have other ways of augmenting the law. So the key advantages here are that the time delay can be freely chosen. This parameter tau introduces a new design parameter. We get greatly improved performance when augmenting a PI controller, P plus I controller. We get greatly improved performance as sudden changes in dynamics or rapidly varying external disturbances. All existing methods of modification still apply, including loop transfer recovery and E-modification. It possesses a natural robustness to unmodeled dynamics even. Now, this is a key point because conventional adaptive control does not have a natural robustness on unmodeled dynamics. And it extends easily to output feedback, and it's especially applicable to adaptive control of large scale interconnected flexible systems. So the key difference in derivative-free is the underlying assumption. The underlying assumption is, in this case, that the uncertainty delta can be linearly parameterized by a bounded set of time-varying ideal weights. In other words, the ideal weights now can be time-varying. They no longer have to be constant. And that was what provides all of these benefits. Okay, so again, I'll go back to those two examples I showed earlier. This was derivative-based with a time-varying uncertainty, which is a square wave. The ideal weight is a square wave, the blue line here. And this was the adaptive design, the conventional adaptive design. And this is the performance we get with derivative-free. And you see, we get excellent tracking performance and excellent estimation of the ideal weight. The estimated weight tracks the ideal weight very accurately. And then this was shows the benefits of adaptive loop recovery. Here in the same example, we're introducing a time delay of 0.02 seconds and showing the responses with and without adaptive loop recovery. So adaptive loop recovery is vital when you introduce time delay. And here to further illustrate how effective derivative-free adaptive control is, we made the WT, instead of a square wave, a sinusoidal WT with increasing frequency. So here the weight starts out at low frequency and gradually increases to an extremely high frequency. And you see, we still get very, very accurate tracking, not only of the command, but also the weight estimate. So this shows the estimate of the weight at the high frequency end. is even at the extremely high frequency end, the adaptive design is estimating the ideal weight. And then this was the example I showed earlier with PI control, augmenting a proportional plus integral nominal controller. Remember, it had this poor behavior during the first 5 seconds, whereas when we use a derivative-free approach with these parameter settings, we get excellent tracking right at the beginning. And this could be very important in the setting of upset recovery when there's a failure in a flight control system. Okay, so to summarize, benefits of adaptive control, it can be used, it provides adaptation to both parametric uncertainty and non-model dynamics, adaptation to uncertainties and nonlinearities in actuation, improved rejection of external disturbances, rapid upset recovery under failures and airframe damage. It permits higher bandwidth design by maintaining adaptation under control saturation with the addition of hedging. Now, this is very important when you get to aircraft like fighter aircraft or hypervelocity aircraft, where you require high bandwidth control. And this is one means to achieve that, even when you have control saturation. And ALR modification, adaptive loop recovery, may be one of the key stepping stones to certification by maintaining the gain and phase and time delay margin of the reference model. I also provide here some recommendations for future research for those of you who might be looking for a thesis topic. Okay, so this is also listed in our textbook as well in chapter 8. So you have adaptation to unmatched uncertainty. Is there an adaptive equivalent to proportional plus integral linear control that cancels the effect of unmatched biases and other dynamic modeling error effects? So proportional plus integral control, the uncertainty does not have to be matched. And so is there an adaptive control approach equivalent to that? No one's ever really solved that problem. There are many properties of derivative-free adaptive control that have not yet been extended to the output feedback case. And they are listed in chapter 8 of the textbook that I mentioned, that's reference 34. Can we develop a more systematic method for selecting the design parameters in adaptive control? And then the final thing is that systematic measures of robustness, things like gain margin, phase margin, time delay margin, are very important if you want to be able to successfully transition adaptive control theory into practical systems. So again, I want to just quickly show you that at the end of the talk here, there's a list of references, but I also organize them according to topic area. So the red there shows the general topic areas, lab experiments, flight tests, technology transitions, output feedback, hedging, reducing the effect of sensor noise, adaptive control theory for flexible systems, loop transfer recovery, derivative-free, adaptive flow. So I've tried to organize all those things. And finally, I want to conclude with a saying that I think is very apropos even today. It's a saying attributed to Hippocrates. I'm sure you've heard that name. It's a philosopher and physician born around 460 BC. And is regarded as the father of medicine and revered for his ethical standards and the Hippocratic Oath. And this is one of the many sayings that you can find in the literature from him, but I particularly like this one. And it's very appropriate for young students to be attentive to this. It is through error that one tries and rises. It is through tragedy that we learn. all the roads of learning begin in darkness and go out into the light. And I derived the meaning from this is don't be afraid to make mistakes. What's important is never give up. Thank you for your attention.
Okay, thanks a lot, Dr. Calise, for your great talk. So with regard to questions, we have, you can unmute yourselves, or you can post your questions to the chat. In the meantime, Dr. Calise, yes, I mean, derivative-free it can be agile. It can produce accurate but agile performance. So it is a nice combination, like how we used in NASA Air Star flight test with adaptive loop recovery to recover the margins, as in addition to the precision we get with the derivative-free.
This is PK Menon. I would talk for Tony here. Can everybody hear me?
Yes.
Hi, PK.
Hi, Tony. How are you? Great talk. I enjoyed it very much.
Thank you.
Thank you. I enjoyed your book also. I'm still enjoying it. The question I have is, when you have, let's say, a neural network in the loop, it's always been a problem for me to decide how many of those units should be in the network.
How many what?
How many neural networks, neurons should be in a neural network? Yeah.
Well, I have a comment on that. And I forgot to mention that if you use the derivative free, because the weights can be time varying, your basis functions could be a simple constant. We've also illustrated that. And so it relieves you from having to worry about how many neurons to have. That doesn't mean you shouldn't have neurons, because the more neurons you provide, the better the performance. But an adaptive derivative-free approach, you can have just a neuron could just be a constant, any constant, one, and we've illustrated that in a bunch of experiments.
Okay, so the thing is, I've encountered a lot of these nets over the past 30 years or so, and I find that a major chunk of some of those nets are basically dead. The weights are just sitting there, not doing anything. So it would be nice to have some kind of an objective criteria where you come out and say, okay, these are the basis functions we need. This is the richness of the basis functions we need, and somehow be able to cull them down, kind of trim the hedge, so to speak, so that you only have minimal set that you actually need.
Yeah, if you have some understanding of what causes uncertainty, like let's say uncertainty due to body angular rates, then you want to include PQ and R as inputs to your and networks. And you may want products of those terms, or you may want products of PQ and R, the body angular rates, with the angle of attack and sideslip angles. So it's pure guesswork. That's correct. And what might be important in one situation may be unimportant in another situation, depending on the nature of the uncertainty or the damage that occurs or the external nature of the external disturbances. So it's a difficult question to address, but it's becoming, by the way, let me also mention, adaptive control, flight control, is becoming a cornerstone in hypervelocity vehicle design and flight testing, because in that case, these hypersonic vehicles fly at extremely high altitudes and extremely high speeds where there's very little aerodynamic performance data. So even when you design the airframe and you go to do a flight test, you can have a catastrophic failure because of the uncertainty is so great in the aerodynamics and propulsion models they used in designing the flight control system. So I think the main area today where there's an opportunity for a full transition of adaptive flight control design is in the hypersonic vehicle area. And again, there it's a lot of guesswork, as far as how to pick the basis functions. But one big advantage of derivative free, it is much less sensitive. One is it's much less sensitive to how you pick those basis functions. And two, it can let you get away with much fewer basis functions because of the fact that it allows for time variant ideal weights.
Thanks very much. Thanks again for a great talk.
Sorry, hi, Tony. This is Wasim Haddad. Can you hear me?
Wasim!
It's very nice to see you, Tony. It's been a while.
Oh, I didn't know you were online today. Thank you very much.
I am. I wanted to ask you a question. One of the issues with adaptive control at Caveat is when you have non-minimum phase zeros or you have unstable zero dynamics when you're doing a nonlinear system. Have you looked at that in more detail? I know when you were here, you and I in Tansel looked at that problem, but we weren't able to do too much with it, unfortunately. But especially when you have safety critical systems and you ask for high gain adaptive controllers, they tend to destabilize when you have non-minimum phase zeros.
Right. That's a big problem area, and I should add that to the list of research areas for adaptive control. Thanks for mentioning that. Well, one thing for sure is when you have non-minimum phase zeros, you should never use an inverting design on such a system.
Oh, yes, absolutely.
But other than that, that's not an area that I've looked into deeply, except for the fact that the JDAM has non-minimum phase zeros in it. And so we had to significantly modify our initial approach to it. It's a very interesting story. Kevin Wise, who was then the lead project manager at Boeing, and Boeing did, provided all the test equipment and all that, and flight tests and so forth. He came to my office one day and using the models he provided for the JDAM, we could not get decent results. And he looked at me and he said, "You have to do your homework." And I didn't know what he meant by that. And he left. He didn't say why. And so we started doing our homework, and we found out, we looked at the transfer functions and it had a non-minimum phase zero. So we did find a way to modify the design using a blend of feedbacks. Instead of commanding, let's say, pitch attitude, we used a blend of pitch attitude and pitch rate and used that as the thing we were regulating rather than pitch attitude, and it avoided the non-minimum phase zero problem. So there are ways to get around non-minimum phase if you alter the output that you're attempting to regulate in your nominal control design. So I can mention that, and that turned out to be very successful.
Thank you, Tony. It was nice seeing you again today.
Hi, this is Dan Wagner with LM. I had a question for you, Tony, and this is, I guess, more general, and that is, how do you necessarily quantify that risk of purely using, like, for example, a baseline linear controller versus an adaptive controller, like at an earlier level? So, like, from my understanding, looking at the JDAM program, that was a little bit more mature in its development before, like, these nonlinear controllers are implemented. But, like, from a cost savings perspective, this was, like, implemented earlier on. Like, what kind of story can be told there? Like, say, like, going to somebody who's totally unfamiliar with nonlinear control.
How to are you asking how to show or convince that person that one should use adaptive control? Is that what you're asking?
Yeah, unfortunately, like I feel like the
Yes.
chances are running into people
Yeah,
who are
okay,
unfamiliar with nonlinear control.
Okay.
Yeah.
Okay. Okay. That, Kevin is a longtime friend of mine, Kevin Wise at Boeing. Now, he was a senior research fellow at the time. Now he's the vice president now at Boeing. And when I spoke to him about adaptive control, he wanted to get adaptive control. And his major stumbling block were the program managers. And I mentioned that in one of my charts. One of the things I always say, why can't we use a conventional approach? So what broke the ice on JDAM was the fact that the military was no longer willing to wait a year to transition the tail kit to a different bomb. They needed a result. They needed something that worked in a month, not a year. So we had that. That became the moving issue on JDAM. The fact that Boeing could not provide a working design within a certain time frame other than 9 months to a year, and a very costly process. Now, when it comes to manned systems, that's a totally different picture, because now you've got the life of the pilot and all the passengers, if there are passengers, at risk when you're doing trying to implement an adaptive system in an aircraft. So unless there is a great motivating factor for doing so, it's very unlikely that it's going to happen, because it hasn't happened yet. However, I mentioned previously, there is one opportunity that I see right now, and that is in hypersonic vehicles. And there's a big movement now to design a hypersonic vehicle, an interceptor particularly. Now, these are unmanned systems, mostly. And the other thing about them is there's a great deal of uncertainty, aerodynamic and propulsive uncertainty associated with such vehicles. We just don't have the data. And so we attempt to do flight tests. We design a vehicle, attempt to do a flight test, and it's a catastrophic failure. And it's happened over and over again. This is the current status of things. This creates a need for something new and different. And that is where I think adaptive control can find another target of opportunity. Now, as more and more of these opportunities work to our benefit, then you can begin to make inroads in other areas to show, look, it's been done here successfully, it made a big difference, and now we should move it more into the direction of more conventional aircraft designs as well.
Okay, thank you. Appreciate the answer.
Dr. Calise, there is a question from Eric Johnson. He put to the chat. I will read.
I can say it out loud if you want, Tansel. It's great to see you, Dr. Calise.
Eric.
Yeah, and
I didn't know if you could actually see me while I was doing the presentation or not, but go ahead.
Oh, yeah, for sure. I'm curious, you've been doing a lot of neat work lately with guided parafoils, and I'm curious I think that's a great platform for adaptive control having a benefit as well as being kind of challenging. And I'm wondering if you've tried that or have any comment on that.
I'm sorry, I didn't catch what you said right at the very beginning. I've been doing work with what?
The guided parafoils.
Unfortunately, all of that work, as far as my role, has come to a complete end about 3 or 4 years ago.
Okay.
And it's really, really sad that happened, because we were really doing some pretty fantastic things, but everything came to a catastrophic end on it. And it's largely outside of my realm of things, it was mostly a business-related issues that arose, and it led to the collapse of the company.
Okay, but it wasn't the fault of adaptive control, I suppose.
No, of course not.
Thank you very much.
Dr. Calise, one more question from Islam Ali. What are the benefits of discrete time adaptive control as compared to derivative-free adaptive control?
What are the what?
What are the benefits of discrete time adaptive control in comparison with the derivative-free adaptive control?
Well, I tried to say those things during the talk. I would, if I had to, it solved two of the problem areas with adaptive control that I mentioned. You know, you don't have the conflict with when you're augmenting a proportional plus integral controller that you have, because derivative-free doesn't involve integration. And the second issue is that derivative-free is naturally robust to unmodeled dynamics, whereas adaptive control is not. And the third one is when you have time-varying ideal weights. In other words, the uncertainty cannot be characterized by a set of constant weights. Derivative-free does not require the ideal weights to be constant. And so if you have, if you have a failure, a structural damage, or loss of control in an actuator, and the uncertainty then has a time varying, it cannot be characterized by constant weights, ideal weights. Derivative-free doesn't require that. So those are the most important things I think about derivative-free. Maybe you could add to that, Tansel.
Absolutely. So since you are on the spotlight, I just didn't want to transfer that myself. So Dr. Calise, we can end the talk now. So if there are more questions, can they email you?
Of course, and I said in the beginning, I welcome this kind of interaction, and I really enjoyed hearing from some of my former colleagues and students. It's been a great pleasure. Oh, Kadri, I finally get to see you. How are you?
I'm so sorry I needed to join really a little late. It's great to see. It was a great talk. I have a couple of students here who are still working with the hedging control sector. I'm sure they are very happy now. Okay. And I would like to say the photo you have from Tansel's group is, I think, from 2017 or something, right? You need to change your group photo.
16 or 16 or yes.
Thanks for this opportunity, Tansel. It's been a great pleasure for me to see hear from former students, and I hope that this leads to more conversations between myself and my colleagues, former colleagues, and my former students. It'd be a wonderful outcome for me.
Yeah, it was wonderful to have you, see Dr. Haddad, Eric Johnson, and everyone, my students, Mervis.
Wow, it was a big surprise. It was a big
PK
surprise.
Menon and Kuan Clement, Ali Turker. Yeah. All right. Thanks everyone for attending, and thanks especially to Dr. Calise. And this is the end of today's talk. Then
I also want to thank Tansel for organizing it. Thank you.
Bye now.
Thank you.
Bye.